Welcome to The Explainer. Today we're digging into the one thing, the single biggest thing that could slam the brakes on the future of AI. And I bet it's not what you think. It's not about silicon, it's not software. Nope, it's something way more fundamental. Okay, so let's just jump right in with this quote because it really flips the whole script on the AI race. We're not just talking about better code or clever algorithms anymore. No, this is about the physical flow of electrons. It's raw power. The future of AI, it's really an infrastructure problem now. And to really get a sense of the scale here, just picture this. Training one big AI model can suck up as much electricity as thousands of homes do in an entire year. And get this, that's just for the training. The energy it takes for all of us to actually use these models, what we call inference, well, that can be just as much or even more over its lifetime. It's staggering. So this insane demand for energy, it's creating this massive challenge that, honestly, most of us never even see. All of a sudden, AI isn't just floating around in the cloud. It's physically hardwired to our planet's power systems. And here's where it gets really interesting. Because it's not just one problem. It breaks down into these real-world physical hurdles. First, you've got the sheer power consumption. We're talking small cities' worth of energy. Then, all those GPUs packed together get incredibly hot. So you need massive cooling systems, which means you're now competing for resources like water. But okay, let's say you solve all that. You still hit this giant wall of bureaucracy. In the US, just to get a new data center plugged into the grid, you could be waiting for years. And that's forcing these AI companies to do something wild. Basically become their own mini utility companies. So what happens when your super advanced AI has to be physically located right next to a giant power plant? Well, the whole map of innovation just gets redrawn. It's not about being in Silicon Valley anymore. It's about what the source material calls cognitive geography. Where the power is, that's where the thinking machines will be.
Let's look at our first example of this cognitive geography. Virginia. You know, it's really not an accident that so much of the internet seems to run through this one state. And this slide just shows you why so perfectly. It's this killer combination of data infrastructure and raw power that creates this gravity-like pull for AI. Virginia already had the undersea internet cables landing there, and it had a super reliable grid. That brought in the data centers. And once they were there, well, that created this powerful feedback loop of jobs, talent, and a whole lot more investment. All right, let's head over to our next case to see how this whole thing plays out differently. Texas. They offer a completely different set of advantages. The key thing to get here is that it's not just about raw power, it's also about policy and the energy mix. See, Texas has its own independent power grid. It's called ERCOT. And because it's independent, companies can get hooked up way, way faster. You throw in cheap natural gas and a huge growing renewables sector, and bam, you've got the perfect recipe for these incredibly power-hungry AI operations. And finally, let's jump across the pond and see how basic things like climate and geography are shaping this, looking at countries like Sweden and Finland. I mean, this just goes to show you that the most basic physical facts, like how cold is it outside, are now huge strategic advantages in the high-tech world. The cold climate in the Nordics gives you free, natural cooling for data centers. Plus, you have all this stable, cheap energy from hydro and geothermal power. It's a natural fit. But, you know, putting all your eggs in a few baskets, that creates a huge risk. When that massive winter storm hit Texas a few years ago and its grid froze up, it wasn't just some local energy problem. No, it was a direct threat to the global computing capacity that had bet big on that one region. A single point of failure. Okay, so even if you find that perfect spot, you've got tons of power, you've got water for cooling, there's an even bigger roadblock waiting for you. Good old-fashioned bureaucracy. This slide just nails the central conflict perfectly. We've got 2020s technology, AI models that can be spun up in months, being choked by what's basically a 1970s-era regulatory system. It's a massive speed mismatch. An AI model can go from idea to reality in a few months, but getting the green light to build a power line for it, that can take a decade, or even more. And we're not talking about small hurdles here. These are fundamental problems. You have environmental reviews that can just drag on for years and years. You have nuclear licensing laws that were written for the atomic age, not for modern, safer reactors. And trying to build a power line across state lines? Good luck. That could take over a decade. And that's before you even get to local zoning fights and people who just don't want it in their backyard. It slows everything to a crawl. So all of this massive bottleneck, It forces us to ask a really critical question. If energy is a limited resource, who gets to decide how we use it? Suddenly, this isn't just a tech problem anymore. It's a social one. Yeah, who gets the power? And what gets built? Because when you control where the energy goes, you're really controlling society's priorities. Every single megawatt is a choice. And this table lays out those trade-offs so clearly. Every megawatt that goes to one thing is a megawatt that can't go to something else. So do we power consumer chatbots designed to keep us clicking? Or do we point that energy towards scientific AI that could help us model climate change or discover life-saving drugs? Right now, a lot of those big decisions are being made by utilities and governments pretty much out of public view. And that brings us to this really important difference. There's engineering efficiency. That's about getting more computing power for every joule of energy, making better chips. But then there's allocative efficiency. And that's the much, much harder question. Should we even be powering this particular use of AI at all? Okay, so if the grid is the bottleneck, what can we actually do about it? Let's talk about the solutions, the policy levers we could pull to, widen the pipe. The source material lays out some really practical, nonpartisan steps that could tackle these delays head-on. We're talking about fast-tracking approvals for new power lines, updating the licensing for those new, safer, small modular reactors, and really investing in grid-scale batteries. These are real, concrete things we can do to get things moving. And that brings us to the key takeaway. I mean, just listen to this. Who gets megawatts today will shape which kinds of intelligence get scaled tomorrow. That's a really profound idea. The choices we're making about our electrical grid, something most of us probably never think twice about, are now literally shaping the future of intelligence itself. And that's really the final thought to leave you with. This whole technical problem of power and pipes, it's actually a question of foresight, of planning, and of policy. The future of AI might not be decided in a fancy lab in Silicon Valley, but in a dusty utility commission meeting somewhere. The grid isn't just the new data center anymore. It's the new policy frontier for AI. The real question is, are we ready for that?